All right, you guys, I'm going to go ahead and get started. Nice to see you again. I hope you enjoyed your long weekend in the same way that I did, which was like pounding away on my laptop. But anyway, we're going to get into pulse sequences today. We got a couple sort of orders of business, a few things to talk about today, but we're going to finally we hopefully understand a fair bit about the hardware involved and the governing equations involved. And we're finally going to get towards talking about like image contrast. We haven't gotten to image formation. That'll come a little bit later, but we're going to talk about how we manipulate the contrast in our signals and how we manipulate signal amplitudes, basically, by a combination of RF pulses and the timing between RF pulses. A couple other things to sort of get on about, a little bit of class business to start with. The first one is about the laboratory, and I hope this doesn't create a problem, but we had some kind of significant scheduling issues on my end, basically, that limit us from being able to do the lab next Wednesday, which is when it was originally scheduled. I'd like to do it on Monday. The upshot to doing it on Monday is I'll keep the due date, so you'll effectively have more time to write your laboratory on top of sort of other things that you have going. Could you, just by a show of hands, tell me if there's an absolute conflict and you are unable to attend during this window on Monday? Okay, so we'll have to talk about your absolute conflict and how to resolve it. We may have to hold a separate laboratory for you or someone else, two people. So it'll probably work out. We'll probably just find a time when you guys can do the lab. I'm sorry for this. It's nothing I can control at this point. And I think Monday looks like it's a reasonable solution. If you guys told me that it collided with a Tuesday midterm or something like that, I'm a reasonable person most of the time. Okay? Okay, so I think we're okay. So then the next order of business is that I want you to forward lists of like 2 to kind of 4 people. We have 3 scanners that we'll work on. I don't know what the total enrollment is right now, but it's in the low 20s. And just as a matter of sort of like what I know works, we can only have kind of 3 to 4 people on each scanner. So if you have someone with whom you'd like to work, email Eric. Eric will put together sort of the lab times and assign groups. If you don't have someone, not a big deal. We'll get you into a group, obviously. But I'm looking to form groups of kind of like 3 to 4 people. So at any rate, if there's someone with whom you'd like to work, let me know as soon as you can, because we want to get this sort of scheduled out. And then I'll assign you guys to times, either the 6 o'clock group or the 7:30 group. We typically stick to this schedule pretty well. The only caveat being that we also have clinical exams that are happening up until about 6 p.m. that sometimes get delayed a little bit. And so 2 things. I ask that you meet me where I'm going to show you in just a second, and that you understand you're coming into a clinical environment, and so there's a high level of expectation for absolute professionalism, right? I wouldn't want a patient to remark in any way, shape, or form that they felt uncomfortable because there was 20 students staring at them as they came out of the scanner, right? So we'll get to that a little bit again on Monday before the laboratory. Bottom line, if there's a group you want to work with, let Eric know, and we'll assemble the groups. If you absolutely cannot be there at 6 and you have to be in the 7:30 group, let me know. If the other is true, you can only be there at 6 and you can't accommodate being in the 7:30 group, let me know. We always make it work one way or the other, but I just need to know what your constraints are so I can do that. Okay?
Should be 25th.
I'll trust you on that. Yeah, it must be. If Wednesday's the 27th, then it would be the 25th. Thanks. You can't do this in your printouts, but I can do it here. Thank you. Okay, so questions about the lab and sort of just the overall organization. I'll send you the write-up. There's not a whole lot of preparation to be done before the lab itself. It's partly an instructional lab. I want you to learn how the scanners are operated. And it's partly a learning lab where you're going to do some experiments and analyze some imaging data. We'll talk more about the lab itself on Monday because we have to get through the next couple lectures. Something I forgot to put a slide in for, but we have lecture this Friday as well. I think it's the last Friday lecture, making up for our Monday holiday. So again, normal procedure, meet here Friday, 1 o'clock, 2-hour lecture. Everything's recorded if that presents a conflict for you. But the lectures on Friday and Monday are relevant to the laboratory, so those are good lectures, I think, to attend. In terms of meeting, I know some of you know your way around the MR scanners and know your way around the suites and things like that. I prefer for you to meet me sort of where I'm designating here, which is outside of Medical Plaza 300 building. You probably know that we're up here buried in a CHS somewhere kind of here-ish maybe. And we're going to meet sort of in the courtyard behind MP300 here. This is just an easier place for me to collect people that don't have access into the MR scanner room. Some of you do, I understand. But if you could please meet me here, it's a little bit better because that way I can be cognizant of what's happening on the clinical side and bring everyone into the MR suites when there's a good time to do that. If that's not precisely at 6, 6:15, something like that, we'll make it work. Okay? Does everyone understand sort of where this location is? The map will help if you don't know exactly. Partner up with people if you need to. University campuses are notoriously difficult to navigate, but this is what's close to Diddy Reese, right? You know where that is. Okay. So clarification, this slide, I just put it back together again. I apologize. In the last lecture, there were some mistakes. I think it's clarified in this slide. I'm not going to go through it again. Other than to point out, we will use this nomenclature today when I'm working through some examples of spin dynamics, what happens to the bulk magnetization as a function of time. And so we'll use this as our initial condition description, and we'll use this as the maximum possible amount of bulk magnetization. So at time infinity, when everything is at total equilibrium, this is the most that you can have. This MZ zero magnetization is some initial condition. The system's been perturbed, and it's the amount of magnetization you have that we're going to begin considering for whatever the subsequent event is. And so we sometimes call it the MZ at time 0 minus. And we're going to work through a bunch of examples today. So hopefully this becomes solidified sort of in today's lecture. And we will talk a lot in this sort of nomenclature today as well. So we'll be keeping track of what happens to the MZ magnetization. We'll be keeping track of what happens to the transverse magnetization. And by 0 minus, we mean immediately before some event. We'll label our events, event 1, 2, 3, 4. And by time 0 plus, we mean immediately after some RF event or after some event. And depending on the pulse sequence, there's different time points that we maybe care to evaluate what's happening with the magnetization. Frequently, it's immediately before and after an RF pulse, but we may want to evaluate the magnetization at some other arbitrary time point. We can just label that time point, evaluate the force and free precession equations, and figure out what's going on. But we'll get some working understanding of using these equations today. This was just a summary of what we really were talking about in the previous lecture, and it was largely about how we can generate additional B fields that we call gradient fields. These gradient fields are called gradients because they vary over space. They have spatial gradients. Importantly, they're B fields that only contribute along the z direction. Ideally, there's some Maxwell terms that we don't worry about. And if we look at their sort of vector notation, we can turn a gradient on in any direction. We can turn on the x, the y, or the z gradient at any point in time. And it will act on a spin at the spin's position, there will be an effective field. And so we know through this dot product expression here, if we're at the isocenter, then the gradients have no effect because the gradient's just being dotted with the 0, 0, 0 vector. And as we move away from isocenter, then the effective B field is bigger and bigger and bigger, either bigger in the positive sense or possibly bigger in the negative sense, depending on what direction you move relative to the applied gradient itself. But the point is that the combination of the B field and the gradient field gives rise to some new B0 field or some new B field that we have to then take into account if we're talking about what happens to the bulk magnetization in the laboratory frame or in the rotating frame. This example here is just a combination of two applied gradients. We have an X and a Y gradient turned on. We're working in the rotating frame, so there's a set of spins that don't have the appearance of precession because they're at the Larmor frequency. And when we turn two gradients on, we'll end up with a line, in fact, a plane of so-called isochromats. And we can steer that plane around just through the different linear combinations of the gradients, turning on just X or just Y, or in this case, an equal combination of the two. And by creating a plane of isochromats, we can imagine that we could have an RF pulse that was tuned to that particular frequency and consequently excite that plane, what we call a slice. And so in this example here, we'd be able to excite an oblique slice that went through the anatomy as shown on the left-hand side here. So this is just a quick overview of how gradients change our magnetic field. And of course, by spatially changing the magnetic field, we spatially change the Larmor frequency, and that gives us the ability to sensitize our excitation to specific spatial locations. We'll talk more about this later when we talk about spatial localization, because this principle here is central to what we call slice selection, or exciting spins just in a slice of interest. Questions about the gradient lecture? Okay. We worked out a little bit, just some expressions for what kinds of phase is generated by the activity of the gradients. And because our gradients can be time varying, and in fact, we'll look at this later in the course, the spin position may be time varying, right? Spins can move around inside the scanner as a function of patient motion or physiology, blood flow, things like this. We know that the phase that the gradients are going to generate just comes from the integration of the effective field times the gyromagnetic ratio, so that the units of this thing that you're integrating is just a frequency, right? Field gradient times position is field, and then field times gamma is frequency, like Larmor frequency, integrated over time, and we can talk about what the gradients are doing to affect the phase of the spins. And what you notice, we could use that B field in the equation of motion to solve for what's happening to the spin system. But what you would end up finding is that the gradients themselves impart a rotation, or they impart a phase on the spin system. That's only a rotation and always a rotation about the z-axis. Okay, so that means that our gradients, by their construction, when they work in this ideal sense, by their construction, the gradients can only act on the transverse magnetization. Okay, there's no action of the gradient on the z magnetization. This column of this rotation operator here tells us that we're rotating about the z-axis, and that means that our z magnetization is unaffected by the activity of the gradients. Okay? And so we can see that through this rotation operator here, which looks very similar to the rotation operator that we would have had for free precession, for example, much earlier in the course. Okay, so that's where we landed with gradients. What we're going to talk about now is how we can manipulate the spins as a consequence of using different RF pulses. And that brings us into talking about image contrast. The last thing I'll mention, I think everyone is here now too, is Patrick will come at about 2:30, kind of end of lecture, to field some questions about the homework as well as myself. So depending on exactly when we wrap, we can take some questions about the homework. And he can stay immediately after lecture. I can't stay for very long today. I could stay for maybe 15 minutes or something like that. But it sounds like you guys have been taking advantage of him in particular at office hours and over email. And if there's remaining questions, then we can try to address those at the end of class. And then hopefully things are winding down and you're feeling good about getting the assignment. Okay. I'm sure you have homework questions. We'll come back to that at the very end. Okay, so our goal today, as I said, was to talk about image contrast. We need a definition for image contrast to get going, and we need to think about why is it that image contrast is maybe interesting in the first place. Well, it turns out as human observers, we're very, very good at detecting image contrast. The human visual system is very sensitive to contrast. We're not very good at detecting absolute luminance. We can't tell you how bright something actually is. In lumens would be a typical measure of light. We're not good at that. As ambient light adjusts, we have a hard time telling you how bright or how dark something is unless it's very, very bright. We can't assign units to it sort of qualitatively very well. And so we're not good at counting photons, so to speak. What we're good at is counting and adjusting for contrast between objects. That's what our human visual system is tuned to do. And so this is an example that some of you have probably seen before, because I use it in the 205 lectures too. It's a kind of unusual looking checkerboard with this green tower that casts a shadow, fine. And the question is, which is brighter, A or B? Meaning in the absolute luminance sense, you think one region is brighter or darker than the other. So who thinks B is brighter? Raise your hand. People don't want to answer, they know the answer. Who thinks A is brighter? don't want to answer because I think that, right. So people think A is brighter, but that's kind of an unusual thing to say, right? Because you're looking at this checkerboard pattern. You're saying, really, you're telling me A is brighter than B? I mean, obviously it's the dark checkerboard square, and this is obviously the bright checkerboard square. You must have lost your mind. Now, of course, we're not good at detecting luminance. We're good at contrast, and so if I cover up B and I slide it over on top of A, we see, of course, that they're equal. And so there's a trompe l'oeil effect here, a fool the eye effect, right? Where we're not good really, although in this you had a Bayesian prior, right? So at any rate, several of you got it correct, but we're not that good at getting and judging absolute luminance. But we are pretty good at detecting that there's clear contrast between these different objects. So consequently, a lot of imaging technologies and techniques have developed along the lines of maximizing image contrast. And much of radiology is still a qualitative field, right? If you ask the radiologists what they do all day, not a lot of numbers involved, right? There's absolutely a lot of qualitatively looking at an image, looking at a series of images and trying to identify what's normal and what's abnormal about, the study that they've been presented with. I'll show you some clinical examples of why image contrast is valuable when we get towards the end of lecture. So we're good at picking up on contrast. Here's just some different examples of sort of evaluating your own visual conspicuity or visual acuity. And we know that large, high contrast objects are simply easier to see in the presence of noise. So here's a large object with high contrast, and it's no difficulty picking it out. As the objects get to be lower in contrast in the presence of noise, it's very difficult to make out. If you had to draw a contour around this tumor, it'd be hopeless, right? And small objects, of course, that are also surrounded by noise can be more difficult to pick out as well. So we like larger objects, and we like to have high contrast, obviously. And so we target imaging sequences that provide us with high signal to noise, meaning the noise is not very evident in our images. And we prefer things that have strong contrast so we can detect boundaries between fundamentally different tissues. There's another effect at play which is related to resolution. And we know, just in looking at these kinds of images, that small, low contrast objects are easier to see with higher resolution. So this faint object, which was very difficult to see previously, we've improved the resolution while keeping the signal to noise the same, and you can faintly detect it. You could pick out a boundary on that object pretty well. However, if the resolution is dropped by a factor of 2 in each direction, the signal to noise is kept constant, it basically falls apart. We have the inability to detect the location of the object or the size or the boundary of the object. So in MR, we're always keen to have higher resolution images, but that costs time. We always like to have higher signal to noise images, but that costs time. So we can't always achieve, high contrast, high signal to noise, and high resolution simultaneously. The patients would be in the scanner for days. So a lot of MR becomes about trade-offs, and we'll talk a lot about these trade-offs as the course develops, but we always have to make a trade-off. And usually one of the fixed parameters is imaging time. How long can you accommodate imaging this patient for? And that's governed by a lot of different factors, right? It's governed by how long does the patient want to be in the scanner? How much does it cost to scan the patient? How much motion is going to occur if the patient's in the scanner for that period of time, and motion will lead to some image blurring. So there's a lot of different sort of factors that go into the final protocol that we would use for imaging a subject. In an MR, it gets to be pretty complicated, unfortunately. We'll work through a number of different examples through the course, but this optimization is quite difficult. You'll get some experience in the laboratory on Monday, and you'll get some additional experience in the second laboratory where you are the optimizer. You're sitting on the scanner, changing parameters, trying to meet a target objective. And you'll find that it's not that easy, even when we limit the number of parameters to just a few. So you'll get some experience with this soon. So what do we mean by contrast? We need to give a definition for what we're talking about in the first place. And this is just taken from the Lauterbur book. It's a perfectly reasonable one. And we here just mean to say that the contrast between object A and B is just related to the difference in their signal intensities, however you're measuring that signal intensity, divided by some reference region. It could be just the signal difference, but usually we normalize by some reference. And that reference might be some standard object that appears in the field of view. It might just be the image intensity of A, the intensity of B, or the mean intensity of A plus B. different possibilities, but oftentimes we normalize by something. And this is just contrast. We're talking about contrast to noise. We'll talk about noise when we get later on into the class. But a central goal in MR is to limit image contrast to a single mechanism. So what do I mean by that? Well, the contrast in MR is fundamentally a function of things like proton density, right? How many protons per unit volume are there? We'll talk more about proton density today, but some tissues are more proton dense than others, right? So lots of soft tissues are very watery. Lung, not very watery, right? It's mostly air or largely air. So the proton density of lung is quite low, and the proton density of, skeletal muscle is quite high. Other parameters that matter in MR include the relaxation parameters, T1, T2, T2 star. We might depend on diffusion, and I haven't included several other things that could be here. Perfusion, flow, susceptibility. There's a bunch of other sort of possibilities. And again, the central goal in MR is to limit your contrast to a single mechanism so that you can say, the difference between those tissues is due to their differences in T1. We've come up with a trick where we can normalize for the effects of T2 or get rid of the effects of diffusion, or they're really subtle and don't matter. And so ideally, we want to limit this contrast in some image to be just a function of T1 or just a function of T2. If we achieve that goal, meaning the image is largely dominated by differences in T1, then in this case, we would call this a T1 weighted image. It will not always be a pure T1 image. There will always be some proton density contrast and some subtle T2 effects or something. But it's dominated by T1, then it's a T1 weighted image. And if we've changed the timing of our pulse sequence such that we become largely T2 dependent, then we call that a T2 weighted image. And we can do this in different ways. We'll get some experience with T1 weighted images today in particular. Okay, so working our way from some conceptual understanding of contrast, I now want to introduce the sort of idea of pulse sequences. Some of you know some of this already. This doesn't take too long. And then we're going to work through, we'll spend a fair bit of the time today working through several different examples and then showing some applications, some research and clinical applications of different pulse sequences. One way I like to introduce pulse sequences is as follows. We have some kind of contrast module, and we have some kind of imaging module. And the idea is that we can have a sequence of events. These could be gradient events, radio frequency events, whatever, but they're executed in a particular way so as to adjust contrast. And we'll see more what that means later, but you can imagine that we're going to play an inversion pulse or a saturation pulse or a series of saturation pulses or something like that. And in some way, we're going to be preparing the magnetization, adjusting the contrast of the underlying tissue, if you will, such that at the time we perform imaging, we get a snapshot of that state of the magnetization. And we don't always, but sometimes think of these as being separate processes. We can prepare the magnetization with a contrast module, and then we can get a snapshot of the state of the magnetization through some imaging module. And for those of you that know a little bit about imaging, for example, this could be an EPI readout, this could be a gradient echo, this could be a spin echo, it could be all kinds of different things. But we think about preparing the contrast and then getting a snapshot or imaging the contrast. In principle, they're linked or overlapping even, but let's separate them out like this for now. Lots of different options for the contrast module, lots of different options for the imaging module. Today, we'll talk about saturation recovery and we'll talk about inversion recovery. And we'll just be keeping track of the bulk magnetization dynamics during both saturation and inversion recovery. And they're effectively a process that's going to prepare the magnetization for the snapshot imaging that's going to come later. We'll introduce that when we get into echoes on Friday and then again on Monday. So how do we keep track of the magnetization's history? We've got a couple things maybe in mind, but it ends up being a little bit by force. I'll show you procedurally how we do this. You're getting a sense for how we can keep track of magnetization in the simulation framework through the homework that you're working on now. So the question is, how do we take these equations that we know already, the equations for force precession, free precession, and use that to keep track of what's happening to the bulk magnetization through a series of what could be arbitrary RF events? I've introduced this nomenclature before. It was much earlier in the slide, and we've used it some already. And the idea is we just want to be able to talk about the state of the magnetization for the nth event. We're going to label our events event 1, 2, 3, 4. And we want to talk about either the MZ magnetization or the transverse magnetization either immediately before or immediately after a particular event. And that event, like I said, could be an RF event, or it could be a gradient event, or it could just be some time point of interest. So we've been considering several things. I talked about this a couple lectures ago. We've been talking about free precession, we've been talking about forced precession, we have relaxation, we've got the lab frame, we've got the rotating frame, a lot of sort of examples that we work through. And we've considered every combination of those. So there's a total of sort of 8 different situations that mathematically are of interest, if you will. When it comes to 219, we talked about this before, but the ones that really concern us is just working in the rotating frame. We're going to hop on the spins and precess with them at the Larmor frequency. And then we care principally about free precession, including the effects of relaxation. And so we want to observe if the spin system is just relaxing in the rotating frame, how do we describe the magnetization dynamics? And we ended up with 2 equations, and we're going to use both of these a lot today. The first one just says that the MZ magnetization as a function of time is the sum of some decaying initial condition and some return to equilibrium. And the transverse magnetization is unstable and it only ever decays. You have some initial amount of transverse magnetization and it just decays as a function of T2 exponentially. So we're going to use these equations a lot to keep track of what's happening during intervals of free precession. And intervals of free precession will just be the time in between RF pulses. We're going to introduce a bunch of RF pulses, and if we play an RF pulse and we're waiting to see what happens, the magnetization's behavior is going to be governed by these 2 equations. When we're talking about forced precession, we won't work too explicitly with this form today. I think you're getting some hands-on experience with that in the homework. But the bottom line is we're going to think about events that change the state of the bulk magnetization to some new state according to some rotation. We're going to choose some simple examples. We're going to work with phases of 0 degrees and flip angles of 90 degrees. And so this matrix finally ends up just being a combination of zeros and ones and minus ones. So we won't actually work in this specific formulation today. We'll just use our arms to understand that after a 90 pulse, the NC magnetization becomes transverse magnetization. More generally, you would need to use a formulation like this if we were using 27-degree pulses instead of 90s or whatever. So this is the basic process that we're going to work through. This is just what I'm calling a typical pulse sequence. And the typical pulse sequence starts with an RF pulse, and then there's some time. Usually we call this the repetition time, or the TR. And there's just some time before you play the next RF pulse. Pretty simple. Play an RF pulse, wait some period of time, play an RF pulse. And in that case, depending on sort of exactly what these RF pulses look like, the bulk magnetization will do slightly different things. What we can define immediately, though, is that our bulk magnetization vector, the whole vector, immediately before this RF pulse, so this is event 1, so it's labeled as event 1, is just the M0 vector. And the M0 vector is just the 0, 0, M0 vector. Okay, so this is going to be always our starting point. The bulk magnetization just points along the Z direction to begin with. And then the question is, well, what happens at the next time point? So at the next time point, we have to have, for example, an RF operator, because we had an RF event, and that RF operator is going to act on the magnetization that we had immediately before the pulse, and it's going to produce the bulk magnetization that we would observe immediately after the pulse. And if we designated what our theta and alpha was, we'd have a transformation matrix, and we can multiply that onto our bulk magnetization vector and get a new vector. And the process effectively continues, but after the RF pulse, we have a new consideration, and that's the effects of relaxation. And so here, we know what that relaxation operator looks like. That relaxation operator was effectively shown on the previous page, decaying transverse magnetization and the return to equilibrium of the MZ magnetization. And we just need to take the bulk magnetization vector immediately immediately after the RF pulse, and we're going to act on it by this relaxation operator, and that's going to give us a new bulk magnetization vector. And because time is a factor in this relaxation operator, this vector can be fully described as it changes from immediately after the RF pulse all the way up to immediately before the second RF pulse. So this is the magnetization immediately before the second RF pulse. And now the process effectively repeats itself again. We have a new RF pulse. And so now we need to take the state of our magnetization immediately before the RF pulse. We're going to act on it by an RF pulse, and that's going to give us a new state of the magnetization immediately after the RF pulse. This is sort of procedurally shown using these homogeneous coordinate operators. We're going to work through it in sort of more rote form today using those explicit expressions for what happens to the MZ magnetization and what happens to the MXY magnetization. So procedurally, does this make sense? We have intervals of, this is an interval of forced precession, followed by free precession, followed by another interval of forced precession. And we're always going to keep those separate. We're going to deal with either forced precession or we're going to deal with free precession. We keep track of our magnetization. Yep.
So in terms of pulse sequence, we usually don't consider the relaxation pulse like during the RF pulse.
Correct. Yeah, that's right. And so these events, what he's pointing out is that this RF event here is relatively short. It might be hundreds of microseconds or milliseconds, and we don't concern ourselves with the effects of relaxation during the pulse. That's an assumption. If you want to be exceptionally careful, we would have to keep track of that. But for the purposes of what we're doing for the next couple lectures, we assume that the RF pulses are very short relative to the relaxation time constants, T1 and T2. Okay, so procedurally, this is kind of what we're going to work through today, but you're going to see me write it out in a slightly different way. So the first pulse sequence I want to talk about is saturation recovery. What's a saturation pulse? Just a 90, right? Taking our bulk magnetization, which at equilibrium points along Z, push it down into the transverse plane. And so we do that with a 90-degree pulse. These terms, we talked about one of them already. We have the repetition time, just the what I'll call the duration of the basic pulse sequence repeating block. And in fact, we'll learn about this later, but typically you would acquire at least one echo per TR. Now, we're not going to talk about echoes today. Echoes are the signals that we actually measure. All we're talking about today is how we manipulate the bulk magnetization so that it has contrast in it. We can talk about also the echo time, and this won't actually come up today. We'll need this more when we talk about spin echoes and gradient echoes on Friday and Monday. But the echo time is the time from excitation to the maximum of the echo signal. So we'll form these kind of signals that are measurable. And the data is actually recorded sort of at the echo time, and that contributes to the signals we need to help form the actual underlying image, if you will. The only thing we need for today is the TR, and then I'll give you some other definitions as we go. So this is the basic pulse sequence. Keep this handy. I'm going to work through it on the slide or on the document camera in a second as well. But the basic idea is we're going to play an RF pulse that's got a 90-degree flip angle. We're not going to worry about the phase. A lot of times in MR, we don't care about the phase. And today, we don't care if it's a 90-degree pulse that tips down to be along plus X or minus Y or something else. And so the basic unit or sequence block that we're talking about is just a 90-degree pulse, instantaneous, right? Very, very short, followed by just time elapsing for a duration TR. And then we're going to repeat that n times. We'll end up with a general solution here in just a second for what happens to MZ and MXY at different time points. I've labeled the time points here. So we have time point 1 is the first RF pulse. Time point 2 is the second RF pulse. Time point 3, third RF pulse. We're not going to carry this out to the nth RF pulse. We'll generalize it as we get partway through. But that's the basic sequence that we're talking about. Okay? Okay. So I cheated a little bit and I drew axes for myself already. But I didn't draw the RF pulses that I need. So the first thing I'm going to do is redraw those RF pulses and the timing and things so we can keep track of it. And what we're going to do on this top axis is keep track of the RF events. And on the second axis here, we're going to keep track of what's actually happening to the magnetization components. You'll see what that means as we go. But what I need to do first is draw in place my first pulse, which I'll just label it as a 90 pulse. I need to wait some period of time, and I'll draw my other 90 pulse. And then I'll wait some more time, and I'll draw my third 90 pulse. Those different pulses, of course, are separated by time TR. You guys have this already, but I need it. And this first RF pulse we call event 1. The second one we call event 2. The third one we call event 3. And obviously we're following along here as a function of time. So the first thing we need to do is define what's the state of our magnetization for the beginning of this process. So we start off with mz at time point 1 immediately before the pulse. So that's the nomenclature we're using for keeping track of this. Am I writing too small or is that okay? It's okay? Okay. So what's the amount of magnetization I have at that time point, my mz component? Yeah, so I think two different answers. Lauterbur says mz naught. And while I hesitate to disagree with the Nobel laureate, I'm going to call it m0, right? So it's the maximum amount of equilibrium magnetization. And then we're also going to keep track, and I'm going to effectively have two columns just so you guys know where I'm headed. I'm going to keep track of the mz magnetization here. I'm going to keep track of the my, or the transverse magnetization over here. So if it helps you keeping your notes clear. So over here, I also want to talk about what's my mxy for event 1 immediately before that first RF pulse, and how much mxy do I have? 0. All right, I haven't done anything interesting yet. Okay, so this was sort of trivial. Those two equations, if you want to reference, those map back to equation 7.7 in the Lauterbur book. So the next thing we need to do is keep track of what happens during the action of the RF pulse. And so we want to talk about our mz magnetization, still for time point 1, but in this case immediately after the pulse at time 0 plus. So how much mz magnetization do I have after a 90? 0. If it's a good 90, right? And that's true for everywhere. Let's do the same thing for mxy. So now I have mxy at time point 1, but immediately after the pulse. And how much magnetization do I have? m0, specifically coming from however much magnetization I had along my mz axis, right? So this process here is just the RF 90. And this process here is just the RF 90, right? And you'll see, and this is going to happen frequently, but you'll see that the magnetization that I had over here, this mz magnetization, I'll refer to it as being inherited, right? It was inherited onto the transverse plane because we put it there. We forced it by 90 degrees into the transverse plane. And this is where the dynamics become really interesting in MR because we can trade off how much magnetization we have along the z-axis and how much we have in the transverse plane. And this gives us fundamentally the ability to manipulate image contrast because we can push the magnetization into the transverse plane. We can also push it back up along the longitudinal axis. We can force it with RF pulses to do different things. And depending on how we adjust the timing and the amplitude or flip angle of those pulses, that'll fundamentally change the contrast of the images that we care about. So the thing to remember here for our mz magnetization is that it's now going to be subject to the equations of free precession. And that just says that your initial condition is going to decay as a function of T1. And you're going to have another term that represents the return to thermal equilibrium, which is m naught times 1 minus e to the minus t T1. And for the transverse magnetization, that's just a general expression, right? And we have something similar for the transverse magnetization where we would say that the mxy magnetization is a function of time. Just depends on some initial condition for the transverse magnetization. It's an unstable state that decays as a function of T2. And so this line here, those two equations, those are just the equations of free precession. So all we need to do is take our initial conditions, plug it into these equations of free precession, and we'll get a state of the magnetization at some later time point, if you will. And so let's talk about the mz magnetization at time point 2, immediately before the RF pulse. So we're headed out in this direction, right? We want to say what's happened to the state of our magnetization as we approach time point 2. To back up just a tiny bit because I haven't been keeping track of my magnetization. So my mz magnetization I'll show in red, and my transverse magnetization I'll show in black. So prior to my RF pulse, which is up until this time point here, my MZ magnetization is just M naught. And so I can draw out my MZ magnetization as just having a constant value up to that point, right? My MXY, or the transverse magnetization, is similar. It's 0 up until the point of that RF pulse, right? What happened to my my MZ magnetization after the RF pulse? Drops to 0. So I just draw it as dropping down here to 0. And here's where I can see that trade-off that I talked about, inheriting the magnetization from the Z magnetization. And so my transverse magnetization goes up to that full value. Okay? So that's where we are immediately after that first RF event. I know things don't perfectly align, but that's the point. So now the question is, where does our MZ magnetization end up as we approach time point 2? And for that, we need to use this equation for free precession, which has those two terms. The first term depends on some initial condition. What's our initial condition? Just 0, right? So this term is just 0, e to the minus t by t1. And our second state here is just the return to equilibrium term, which is 1 minus e. Now here we know the time that's elapsed from time point 1 to time point 2. It's just the tr. And so I'll write this explicitly as the tr by t1. Make sense? So we kept track of what's happening to the magnetization. We could draw it out as well. And it just means that our MZ magnetization, it's going to return to equilibrium, but only in an amount accommodated by a time tr, depending on the tissue's T1. So let's assume it doesn't get all the way back to the equilibrium state. I'll draw some point, and now I'll draw an exponential recovery to that point. And so that's what my MZ magnetization does. It tries to get back to M naught, but depending on the T1 and the TR, it probably doesn't get there. Could get there. The other thing to keep track of then is what happens to MXY. And again, this is time point 2 immediately before that next event. So what happens to our magnetization is governed by free precession. There's no RF pulses acting. We're just watching the magnetization decay, essentially. What's our initial condition for the transverse magnetization? Just M naught, right? And so it's just M naught e to the minus TR by T2. And so I can draw my magnetization vector again. Now in this case, my T2s are pretty short. They should definitely be shorter than my T1. So I need to show exponential decay of my transverse magnetization that's more rapid than my T1 recovery. And so I'll draw this as a decaying exponential that comes down, and then it's maybe very close to 0 by the time I get to my next RF pulse. And in fact, this term here will in fact be equal to 0 under certain conditions. So if, for example, if your TR is much greater than your T2. So if there's enough time can elapse, several T2s, then that signal will effectively be decayed and my transverse magnetization will disappear. And that's actually really interesting, right? Because that means you've done something to your signal where you've annihilated effectively one component while you still have the other component. So we have an MZ component that's below M naught, and we no longer have an MXY component. It'll depend exactly on the conditions and whether these conditions are met, but you can see it mathematically happen. Okay? So I want to talk about this condition a little bit here. This condition is related to what we call the saturation condition. And so I'm going to flip back to the camera, unless there's, or sorry, back to the slides, unless there's questions about how I've worked through the magnetization. We're going to do this a bunch. We're going to do this for another example today, and then we'll do it for a couple other pulse sequences so you get some experience with how we do it. And you'll grow to appreciate that either this is really interesting and fun and nice and lovely, or you hate it, but that's the way it goes.
So are you basically losing energy since your transverse magnetization is going to 0?
Yeah, so I wouldn't say that you're losing energy per se. I think the picture I want you to have in your mind is this process of transverse magnetization decay right here, right? What that represents is the component of the bulk magnetization is basically fanning out. You've got billions and billions of these atomic nuclei in some voxel. And they're going to be spreading out from one another as a consequence of T2 decay. T2 decay was spin-spin interaction. So the individual magnetic dipoles still have a transverse component, but their sum is now zero when you add it up over billions and billions of these things. Does that make sense? What's happening is that if we go all the way up to this time point here, if I drew a picture of my transverse magnetization, the state of my transverse magnetization would be that all the magnetization was pointing along a single direction. I've drawn it arbitrarily here as just along some direction. Okay? When we get to the point of having T2 decay, two things have happened. One of the things that's happened is that those individual magnetic dipoles are now fanning out in different directions because they're interacting with each other's fields, and that's causing them to lose phase with one another. So this is the sum of billions of things pointed in the same direction. The sum of billions of things pointing in different directions is going to be zero. And so I effectively have no more bulk magnetization. Does that help? Okay. So let's go back and talk about sort of these conditions of when the transverse magnetization can totally decay and what the implications are. And then I'm going to come right back to the document just as it is. Okay, so what I want to talk about is a saturation condition. And the saturation condition just states this. It just says that the MZ magnetization for some time point immediately after, so think of an RF event, so immediately after some RF event is zero. Then you've met the saturation criteria, okay? Now that may seem obvious. We said, well, we had a 90 pulse. We played a 90 pulse that tipped our MZ into the transverse plane. My MZ after the 90 pulse must be zero, right? Well, it depends because your transverse magnetization may be non-zero, okay? So MZ is, what that statement is saying is that MZ is zero after the event, in this case, the RF pulse. How is that possible? Well, it's true, this is possible, so to speak, if the transverse magnetization is gone before the next RF pulse is applied, okay? That means you would have no transverse magnetization that could be converted to MZ magnetization. So remember, my MZ magnetization points up, but I could have some transverse magnetization, right? We don't know. Depends on the history of RF pulses. Now I play a 90, and my MZ component has gone down, the one I was pointing along MZ, but if I had some transverse component that also sees a 90 pulse, it could get tipped up along the Z-axis, okay? So think of having two components. I have a Z component and a transverse component. And as I tip over the Z component, I could be effectively tipping up the transverse component. So this so-called saturation condition, where the MZ magnetization is zero after an RF pulse, that's only possible if there's no transverse magnetization that can get tipped up into the Z-axis. Okay? Don't get too locked up trying to think about what individual magnetic dipoles are doing. Mathematically, we have a Z component and a transverse component. If my transverse component is non-zero and I rotate it, I'm going to have a Z component, or I could have a Z component. My MZ component, this one I started with, might go down to zero, but there's this other component that's getting tipped up. Should draw an animation for that one. Question? Yep.
Yeah, like let's say that there is some sort of magnetization in the transverse plane.
Yep.
How do you tell where it's going to end up? Because
yep.
It has to be like perpendicular to.
Yep. So that goes back to the phase of the RF pulse.
Yeah.
Right. So think of the transverse magnetization as being basically like a pancake, right? It has some magnitude and it has some direction too, but it could be sort of anywhere in that plane.
Yeah.
The RF pulse, the phase of the RF pulse. I'll just use one hand so I don't lock up my joints. You have the transverse magnetization. I can flip that magnetization, say, around the axis of my arm, and that would be one phase for the RF pulse. Or I could flip it maybe along the axis of my arm, and that's just a different RF phase. Both of these pulses I just showed you are 180s. So if you keep track of this finger as the Z magnetization, I can invert my Z and flip the transverse magnetization, but I can also flip it a different way. So the difference between how I flip that pancake or how I flip that transverse magnetization, the flip angle is the same. They're still 180s, but what's different is the phase. We'll come back to that because when we talk about spin echoes, it'll be important. Okay? Okay, so in order to have no transverse magnetization that can be converted to MZ, we maybe have to have a condition like I was just talking about, where the TR is much longer than the T2. So there's a lot of decay, right? That transverse magnetization component can decay. And remember, this is not a conventional sort of vector, right? The transverse magnetization decays with one time constant, and the MZ magnetization grows with another time constant. So I can, at different points in time, have no transverse magnetization and some positive MZ. There are time points where I can have no MZ and have some transverse magnetization. They're effectively independent in some sense. Mathematically, they keep getting linked, but it's possible to achieve those different states depending on this train of RF events. Sorry, that somehow got replicated. So what if your TR is not a lot longer than your T2, right? And this is the state I was talking about a second ago. What if your TR is just, a couple T2s? T2 is 50, 80 milliseconds. What if my TR is 200 or 300 milliseconds? Then you'll have transverse magnetization that can be tipped or converted back to MZ magnetization. And that's potentially going to corrupt or complicate things. In the ideal sense, we want that transverse magnetization to disappear so that we don't have to deal with it anymore mathematically. It just goes to zero, and this simplifies our system. But in principle, you can tip it back. There are other ways of dealing with this. We don't always want to use long TRs. Long TRs mean long imaging times, and we don't want long imaging times for the purposes of how long patients are in the scanner and how much it costs to do things. There are other strategies we'll talk about later called spoiler gradients. Remember, gradients act on the phase of the magnetization. I can use a gradient to actively dephase my magnetization and cause the spoiling effect that I was showing you with the magnetization going in all sort of possible directions. So there are some negatives to doing this, and then of course people have come up with some solutions to how to deal with situations where your transverse magnetization is not zero when you would like it to be. And I'll show you in just a second, there is a steady state solution that's going to arise. We're going to work through just a few more steps of keeping track of the magnetization, and we'll see that the magnetization just keeps doing the same thing if we keep using 90s with a fixed interpulse time, if the TR is fixed. Okay, so I'm going to go back to this example. I'm just going to start off where I was just a second ago. Yeah. We'll work through just a couple lines here, and then I think that'll, we'll see. That might be a good time for a break. Okay, so we just kept track of where the magnetization ended up immediately before this the second 90 pulse, and now we just want to follow through this a little bit further. And so the question is, what is our MZ magnetization at time point 2 immediately after? And here, we're taking our, we have as our initial condition our transverse magnetization, right? And so the state of this magnetization, because it's a 90 pulse, we're effectively tipping up the transverse magnetization from time point 2 immediately before the RF pulse. If I play a 90 pulse, I'm going to take my transverse magnetization and tip it back up onto the z-axis, if you will. But we said just a second ago that the result of waiting long enough, having a long enough TR, is that this component of our magnetization is actually 0. And that's a useful thing in terms of keeping things simple. If we go to the other side now, we want to say, well, what happens to MXY at time point 2 immediately after the RF pulse? And that means that we have to inherit our MZ magnetization. We're going to be taking our MZ magnetization, however much we had, and tipping it into the transverse plane. So we know that this just looks like MZ at time point 2 immediately before the RF pulse.
So that's just coming in from here. This is that exchange of magnetization again, if you will. And this magnetization goes here. This is because we're using 90s, right? So we can take our transverse magnetization, tip it up to MZ, or take our Z magnetization and push it down into MXY. We're doing the latter right now. We're taking however much magnetization we had, we're pushing it down into the transverse plane. Effectively, no time has elapsed. And so this magnetization is just M0, 1 minus E to the minus TR by T1. And that maps back to equation 712. Not quite yet. Sorry. Almost. One more step. Okay, so now we know what's the state of the magnetization immediately after the second RF pulse. These conditions here become the initial conditions for then the next period of free precession, if you will. So we can generalize this a little bit, and we can say, well, mz for time point n immediately before the RF pulse just depends on some initial condition, mz magnetization from the previous pulse, immediately before, rather, the previous pulse. That's the initial condition. It's not stable. It decays as a function of e to the minus, say, tr by t1. And then we have to have that return to equilibrium term. It always looks, or typically looks exactly the same. It's governed by m naught and the time that's elapsed, which is just 1 minus e to the minus tr by t1. This expression here, we can see just from before that the MZ magnetization immediately after the RF pulse is always going to be 0. And so for any pulse, this term just goes to 0. For any series of pulses, that term is going to go to 0. We're working towards this kind of general result, right? And so just rewriting, that means that our MZ magnetization for time point n immediately after the RF pulse is always going to look like M0, 1 minus e to the minus tr by t1. And that is going to be true for everything but the first RF pulse. So that's going to be true for n greater than or equal to 2. And that maps back to equation 7. So it's only during that first interval that the magnetization does something different. Thereafter, the amount of recovery is fixed between the TRs, and we just keep entering into the same state after the 3rd, 4th, 5th, 11th, 112th RF pulse. I can maybe convince you of that a little bit when we look at the drawing of what's happening to our magnetization. During the first 2 RF pulses, the recovery was up to a certain point. I'm only ever going to recover for the time accommodated by the TR. At time point 2 here, my MZ magnetization is going to tip back down to 0, right? We're playing a 90 pulse. And now my magnetization is going to recover again. Now, it's not going to recover as high up as it did before because it doesn't have as much magnetization as it did before. So it's going to get to some slightly lower point at time point 90. I'll draw this as an exponential to there. And that block is just simply going to repeat itself for, all subsequent RF pulses. And so I could draw this identically. The relaxation is going to look the same between the 3rd and the 4th and the 5th and the 6th RF pulses. We can look at what happens to the transverse magnetization also. My transverse magnetization was 0, but I played a 90 pulse. So how much did I end up with? Do I get all the way here? I got all the way up to M naught. Do I get all the way back up to M naught? No. I can only go as high as the available longitudinal magnetization. So this magnetization is going to flip up precisely to there. So I've taken all my longitudinal magnetization, converted it to transverse magnetization. And now my transverse magnetization is simply going to decay. It's got a short time constant, and so it decays to 0 by the time I get to the next 90 pulse. So you can actually go back and take these expressions that we wrote for MZ and identify where they're occurring at sort of different points here, but it obviously just corresponds to being before or after the first or the second RF pulse. We said before that our transverse magnetization is going to decay to 0 if our TR is much longer than our T2, and this helped us meet that saturation condition. The saturation condition is actually shown it arises as a consequence of this magnetization going to 0. Let's just wrap up with what happens to the transverse magnetization in the general sense. So this is what it was immediately after the second RF pulse. We could write more generally that the MX magnetization for the nth RF pulse immediately after the RF pulse is just M0, 1 minus e to the minus TR by T1. So it just looks a lot like the magnetization that we had here. That can't be right. 9.2 immediately before the RF pulse, that's fine. And then that transverse magnetization gets converted onto the z-axis after the 90 pulse. And so this expression here, this is going to be true also for n greater than or equal to 2. And that maps back, I meant to put this here, this is equation 12 there. Yes?
MC between 1 to 2 and 2 to 3 of same height. 1 joule is 1.
From here to here?
No, just at time point 2, 0 negative.
Yep. Oh, to time point 3, 0 negative?
Yeah.
Yeah, they won't be the same. They will be the same. You're right. You're right. They're the same. Because effectively what we're doing, it's a good point, what we're doing is starting from 0. Right? So the initial condition for the MZ magnetization is 0 immediately after the first RF pulse, and it's again 0 immediately after the second RF pulse. And so I said it incorrectly. And the bottom line is the magnetization should come up to the same time point. And it's hard to draw, right? But it should match this time point here. And that's what's seen in this expression here, that the available MZ magnetization immediately, before the RF pulse is always going to be M0 governed only by TR and T1. Okay? So let me go back. We're getting a little tight on time here. Let me go back to wrapping up the saturation slides and then see where we land. What we ended up with was an expression for the MZ magnetization that depended on some initial condition and on TR and T1. This is the contrast module that we were talking about very early on. And this means that the magnetization at some position is going to depend on the tissue's T1 and then how much time has elapsed. We'll learn more about the signals that we record later, but one signal that we can record is what's called the FID, or the free induction decay. And that's this amplitude of the FID. It represents the signal amplitude immediately after that 90-degree pulse. And so our signal amplitude is governed by this equation here. We use rho to indicate the proton density, and the amount of MZ0 magnetization that's possible is just dependent on the proton density. So if you have a low proton density, then all of those curves I drew would just have to be lower, because you could have a different amount of proton density for lung tissue versus muscle tissue or something like that. And ideally, if the process of imaging doesn't perturb the magnetization, then we can actually recover an image that's proportional to
the proton density multiplied by this T1 weighting term. Okay, so a couple things to sort of point out here. The final image, and we haven't learned about how to form the image yet, but the final image is a product of the proton density, right? Proton density is not constant over space, and some function of the T1, and T1 is not constant over space. And so we talk about wanting a T1 weighted image or a proton density weighted image. We can form the proton density weighted image only in the limit of our TR being very, very long. So if our TR is very long compared to our T1, then this term will effectively go away, and you'll be left with just the proton density term. So forming a proton density weighted image, we can do. You can have effectively pure proton density weighted images. If our TR is anything other than very, very, very long, let's say it's short, hundreds of milliseconds or something like that, then we have a significant non-zero term here that multiplies with whatever the underlying proton density is, and that gives us the image that we actually read. So in this case of this saturation recovery experiment, there's only one parameter that adjusts the contrast, right? The proton density is governed by the tissue, and the T1 is governed by the tissue. So the only thing you as a user could control would be the TR. What it means for this particular sequence is that long T1s will be dark. Long T1s are usually fluids like CSF, and short T1s will be bright. And short T1s are usually things like fat or tissues that have contrast enhancement. So you can think on those two ends of the spectrum. So it's a nice sequence in that it's really simple, in that there's only this TR parameter to be adjusted. But it also means we couldn't get T2 contrast out of it if we wanted to. It's not available in this particular sequence. Not based on the equations that we're showing you. We talked before about actually really caring about contrast, so we could actually define how to achieve maximum T1 contrast. There's an exercise in the book that actually goes over this, and if you know what the T1 of species B is, and you know what the T1 of species A is, then you can calculate the optimum TR that will give you the maximum contrast. You can imagine if the TR is really, really short, you'll get one form of contrast. If the TR is really, really long, you'll get proton density weighted contrast. If you want the optimum contrast, you can in principle calculate what TR you should actually be using. And so when you get to the scanner, it's oftentimes useful to know expressions like this, because we usually have a ballpark for T1s of different tissue types, and we could then optimize our choice in TR if contrast was our goal. I'll talk through just a couple applications, and then given the time, I'll probably not have time for a break. Saturation recovery, so the sequence where we're going to be playing saturation pulses. Now, we could, in principle, use an imaging experiment at any time point after the saturation pulse. We could image immediately after the saturation pulse, or we could image many time constants later, seconds later, or hundreds of milliseconds later. In principle, that imaging module can come at any time point after the saturation pulse. They're useful. The saturation recovery sequence is useful for increasing T1 contrast, so we can really separate out contrast if we know the two T1s. And in fact, we also know that we can get proton density weighted contrast from the expressions I showed you before. There's useful ways to use these so-called saturation pulses, and I'll show you some examples of using them to null blood. So we might want the blood signal to be very, very dark, and that will help us see things if we can get rid of the blood signal. Or we might want to get rid of the fat signal. We're not sure if something that's bright is fat or if maybe it's something else, and diagnostically, fat's usually pretty benign. So if we can say, nope, that's fat, probably it's going to be less of a problem. And you can, in fact, I might go through this example quickly today, but you could use it to measure T1s. So you can imagine you've got this T1 recovery term as you're going back to equilibrium. I can get images at different points along that curve and actually work out what is the T1 inside an individual pixel. Let's talk a little bit about something called inflow enhancement. This is kind of an interesting phenomena when you use multiple RF pulses. Every imaging experiment is comprised of lots of RF pulses, dozens, hundreds, thousands of RF pulses. If you think of the RF pulse is going to generate some transverse magnetization. So after the first RF pulse, we're going to generate some transverse magnetization. And pretty much regardless of the tissue type, unless you're talking about something like lung, the proton density is pretty similar, then each of these different tissues is going to generate a large amount of relatively equal transverse magnetization. What's different is how much transverse magnetization you have after you play a series of RF pulses. You might play many, 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 many RF pulses, dozens, hundreds. And if you play those RF pulses repeatedly, the available amount of transverse magnetization will be different for different tissue types. You'll hit what's called a steady state. And short T1 species will be relatively bright, and longer T1 things like static blood will be relatively dark. So this is the available transverse magnetization accords with the available signal or pixel intensity, if you will. Now, just to show you sort of an interesting effect, if you have, in fact, flowing blood, so the RF pulses are exciting a slice. They're only exciting the slice. They don't excite spins above the slice or below the slice. Then there's going to be spins that flow into the slice, right? It's blood that's moving around. We're only exciting this slice. We didn't excite the blood that was outside of the slice, at least initially. The consequence is that things that are flowing, they only ever see a few RF pulses, right? They only have a residence time in the slice of maybe a few TRs. And consequently, the blood only sees a few RF pulses. And because it's continuously replenished, the flowing blood signal stays quite bright. This ends up being its steady state is somewhere way up here, because it only sees a half dozen RF pulses. Whereas things that are static, tissues that aren't moving around, they end up getting the true steady state signal, which is this sort of saturated amount of transverse magnetization. And so we can see this when we look at images. This is just one example. This is a cardiac image here, and you can see that the blood signal here was quite bright. And you wouldn't know it unless you know what the T1s and T2s are, but in this case, the blood has a relatively long T1, so if we're at static, it should be quite low in total signal intensity. But because it's continuously flowing into that slice, it only ever sees a few RF pulses. It's actually this, it's getting this transverse magnetization that's closer to this sort of inflowing blood. So an interesting consequence of playing a train of RF pulses, a series of RF pulses generally drops the state of the magnetization to some steady state. But if you have spins coming into your slice, renewing the available spin population, then the signal can be quite bright. So here's a way that we can use the sort of flow effect to our advantage. Imagine that we want to do imaging in this volume here. This could be a slice or it could be a series of slices, doesn't matter. And as you well know, arteries generally flow in one direction, and then the neighboring vein generally flows in the opposite direction. So I could place a saturation band, and a saturation band would just be a series of 90 pulses. I just play a 90 pulse, play a 90 pulse, play a 90 pulse. And that's going to act on both the arterial spins, but also the venous spins. But it's only the venous spins that are then going up into the volume that I'm going to image. And that's kind of cool, right? Because that means that the saturation pulses plus some T2 star decay lead to signal loss from blood that's flowing into the imaging volume. So these spins that are in the vein are saturated repeatedly, so the signal's driven down. And now there's some time before they arrive into my slice, and they're going to decay because of T2 star. And so now this means that venous blood in that slice will be very, very dark. And I can separate out what's a vein and what's an artery. I can do the exact opposite thing. I can switch the location of things. I can put the saturation band upstream, if you will, and move my imaging volume down. And now my saturation RF pulses are acting on the arterial blood. They're also acting on the venous blood. The venous blood just goes off to a location that I'm not observing. This arterial blood gets saturated, it decays because of T2 star, flows into my slice, and it has the appearance of being quite dark. And so by moving around the location of these sat bands relative to your imaging volume, you can in principle cause the arterial blood to be very, very dark or the venous blood to be very, very dark. In practice, it looks a little bit like this. So here we can see the joint, this should be the internal common carotid and the jugular vein. So this is an axial slice through the neck. When you play no saturation pulse, both arteries and veins look pretty bright. The blood's coming in from opposite directions. It hasn't seen that many RF pulses, so it's got a lot of signal available, so to speak. The other static tissues have now seen hundreds of RF pulses, and their overall signal has hit some steady state that just is going to be relatively low. if we turn on that arterial sat pulse, I can cause my arteries here. You can see a nice round artery here, right? That artery is caused to be very, very dark because you have an arterial sat pulse on. So this is probably the most clear example here. You can see it here as well, where that artery that was here has effectively disappeared. Similarly, we can turn on the venous saturation. And so now we can see, is labeled, yep. So here you can see the opposite contrast, where one vessel is bright and the other vessel is dark. The venous, there should be a vein, for example, right here that was a bright signal in the unsaturated image, and now this vein is made quite dark. We could also do something slightly different I didn't show you. I could put a saturation plane above and below my slice, and then any blood flowing into from the top or into from the bottom will be saturated, and now I have very little signal coming from either arteries or veins. And so, diagnostically, it can be useful to isolate arteries from veins, and to then these so-called techniques where the veins can be dark may allow you to see things that are in the veins that are not blood. So thrombus, for example, or plaques in arteries, for example. So a nice application of using saturation pulses to manipulate the spin signal. I've got a couple other examples in here, but I want to get through quite a bit more material. So the other examples that I have in here, I'll let you guys look through just as examples of how the technique could be used. So there's just a few examples there of how you could use this for measuring T1. As radiology moves from being a qualitative field to a quantitative field, actually measuring and knowing the T1 of a pixel, or a tissue rather, is an interesting, potentially interesting diagnostic tool. So people are working on different techniques for doing that. What I want to do, and I'm doing this for two reasons. I'm going to keep going, in part so we can get through this material, and in part maybe have some time for questions about the homework as well. So the second pulse sequence we want to talk about is inversion recovery, and it just looks something like this. This is in fact images from what we'll learn about later, which is the spin echo imaging sequence coupled to the inversion recovery sequence. And so here we're starting with, what I'm showing you is the magnetization starts at M0, whether you're gray matter or white matter. We play an inversion pulse so that your magnetization is totally inverted. And I could in fact image basically at that point in time. I take my bulk magnetization, I invert it, and get an image right away, milliseconds later. If I did that, if only a few seconds has elapsed, so this is what's called the TI, or the inversion time. So there's only 25 milliseconds from when I played my inversion pulse to when I acquired my image. In doing so, I get a really flat image, very little contrast, because at this point in time, everything's really just proton density weighted. And we don't have big differences in proton density for soft tissues. The only thing that really stands out is the skull. The skull is dark because it's not really NMR sensitive. We go out to a slightly later time point, for example, here. Now I've played an inversion pulse, but I wait 200 milliseconds, and my contrast has developed, right? Think of it like film. You have to let the film sit for a certain amount of time to develop. Here, I've inverted all of my magnetization, and they're recovering along slightly different recovery curves because T1, white matter has one T1, gray matter has another T1, and I can see some subtle contrast now between white matter and gray matter. And this would be an example of a T1 weighted image. I can move out further, and if I move out to just the right point in time, I can see that my white matter recovery curve, for example, has gone precisely to zero, or very close to zero. And now that means that all my white matter signals are going to be very, very, very dark, right? That specific point in time, if I wait 500 milliseconds after my inversion pulse, so I invert, and half a second later I form an image, the recovery of my white matter will go right through its so-called null point, and I'll get dark white matter and relatively bright gray matter, giving me a tremendous amount of contrast, image contrast. I can go out to another time point. I could play an inversion pulse. I could wait 1,000 milliseconds, and now I also have contrast between white matter and gray matter, but if you compare it to what I had earlier, it's somewhat inverted, meaning that now the white matter, which is sort of, the white matter is everything that appears very, very dark in this image. Here, the white matter is relatively bright, and the shining gray matter is kind of gray, if you will, and that's in distinction to what happens with a short inversion time. where the gray matter is kind of bright and the white matter is relatively gray. Yep.
For these images, it looks like different contrast is coming from varying amounts of MC magnetization.
Yep.
But you told us earlier that MXY is.
It's a great question, so I'll repeat it just so everyone's on the same page. All I'm showing you here is the MZ magnetization, the history of MZ magnetization. I play an inversion pulse, and this is what my pixels will do. Now, I'm imagining that we can do it exactly like this. It's pretty close to true, that we can get a snapshot, right? I can somehow form an imaging experiment to give me a snapshot of the magnetization at those points in time. Avinash's question was, well, hold on. You're showing what's happening to the MZ magnetization, but you told us earlier that the only thing that we can detect is the transverse magnetization. So what gives? And what you need to then imagine is that, let's say at this point in time right here, my magnetization has begun to recover back towards equilibrium. If I want to form an image, I now have to play an RF pulse. I have MZ magnetization, and in fact, this is a really interesting state, and we'll see this in just a second, but my transverse magnetization what's my transverse magnetization after an inversion pulse? 0. What is it a millisecond later? 0. What is it 2 milliseconds later? 0. What is it 100 milliseconds later? 0. I didn't have any transverse magnetization, and the only way in the free precession equation tells me it's just my initial condition decaying. 0 times the decay. So the process of relaxation after an inversion pulse is the bulk magnetization just recedes exactly along the z-axis. You're never going to have any transverse magnetization. Hold on. How are you going to form an image? Well, to form an image, you now have to do the imaging part of the experiment, and that necessarily requires that you play another RF pulse that will then tip the magnetization into the transverse plane to be detected. But what you're effectively doing is tipping the magnetization over, it's like the cosine component of the magnetization, into the transverse plane. So the amount of transverse magnetization now will be geometrically proportional to how much MZ you had just a second ago, or a microsecond ago. And then you'll get a snapshot of your magnetization. So you're exactly right. We can't exactly see it here. We have to take the state of our MZ magnetization, project it or push it into the transverse plane instantaneously, and form an image. And we'll talk about how we do that with a gradient echo or with a spin echo. Yep. Question? No. Okay, I'm going to keep chugging along here. We can do this in any plane, no big surprise. So just some axials and some coronals showing the same pulse sequence parameters, the same inversion times being used to capture the magnetization dynamics in different planes. So this is the pulse sequence that we need to work through. This is the last thing that we sort of have to get through today. I'll work on the board in just a second, but this is the sequence of events that we're talking about. We've got an RF pulse that's a 180. That means we're going to invert our transverse magnetization. And you'll see mathematically, you'll see what I was saying a second ago. The magnetization is only going to recede along the z-axis. We're going to play an inversion pulse. We're going to wait some time ti, and then we're going to play a 90 pulse. This 90 pulse could be useful for forming the image, for example. All right, this will generate some transverse magnetization that's detectable. We might detect that magnetization by forming an echo at some point here, and then necessarily we're going to repeat this event. We're going to play another inversion pulse, maybe play another 90, go on and on and on. So this is the repetition block. Inversion pulse, wait some time, play a 90. And the 90 in this case, you can think of it as a saturation pulse. It's still a 90. Sometimes we call it an excitation pulse, because we're using it to generate that transverse magnetization that will let us sample the MZ magnetization. Questions about where we're headed?
So basically, so far we are talking regarding the contrast module, but this spin echo, this part is the imaging module.
There's no imaging module quite yet. All I'm showing you is the inversion pulse, and then a 90 pulse will generate some transverse magnetization. And we'll talk about what the transverse magnetization looks like as a function of time, but we haven't talked about like refocusing pulses or alpha pulses that are needed for the imaging part. We're really close, but we're not quite there. Okay? Okay, let's see if we can work through this next one. Takes me a sec. Let me give you a 2-minute break or 3-minute break if you really need one, because I got to swap over my paper up here, and then we'll be off to the races.
I'm just going to start drawing a couple things that are related to the diagram that you guys already sort of have in place, but just so we're all on the same page. On my RF axis, I need to draw my 180 pulse. And then at some later time, I need a 90 pulse. I'm being a little sloppy with my nomenclature, but I think you guys get the idea at this point. And then I'll wait some other period of time, and I'll play another 180. And then I'll wait the same amount of time before I play my 90 pulse. I'm going to label a few things, the time between RF pulses, between the repeating block, rather. I'm going to play the same pattern over and over again. That's my TR. I have the amount of time. I'm just drawing the picture that you already have in the slides. The amount of time we have here from the inversion pulse to the excitation pulse, we call the inversion time. I think I don't use it today, but sometimes we call the time from the 90 to the 180 the TD. And obviously, TI plus TD equals TR. This, of course, is my time axis along here. And I'm going to keep track of these different events, so I'll label them. This is event 1. This is event 2. This is event 3. This is event 4. First thing we need to do is talk about what the state of our magnetization is. Sorry. And so I want to say what's happening. Oh, let's see. Hang on. I'm going to need some space here for a minus z-axis because our bulk magnetization is going to be inverted potentially down to minus m naught. Had to squeeze that in. Sorry. Okay, so the first thing is, well, what happens to, or what is our mz at time point 1 immediately before the first RF pulse? You guys know this, right? Just m naught. Thank you. Do the same thing for our mxy magnetization. I'm going to need some space later. Hopefully this works. I'll put it over here kind of far. So now my mxy magnetization for time point 1 immediately before. How much magnetization do I have? 0. This all starts off the same. The first 2 steps are easy, right? Now, the thing that's different from the previous time is now we're playing a 180 pulse. So we have our mz magnetization immediately after time point 1. How much magnetization do I end up with? Negative m naught. In my mxy magnetization, this is what I was talking about before. My transverse magnetization immediately after the inversion pulse, 0, right? It didn't land there. Didn't end up with any. So let's see what that looks like if we draw it out qualitatively. This is my mz magnetization. My mz magnetization is just cooking along at m naught until I hit the inversion pulse. And as soon as I hit the inversion pulse, it's going to go down to minus m naught. And that's the point that I'm at right now. My my transverse magnetization, rather, hasn't done anything very interesting. It started off as 0, and it just stays as something like 0. So not too fun yet. So the next thing is this will become the initial condition for our next state, if you will. We want to talk about what happens to our mz magnetization immediately before time point 2. So it's just going to be recovering until we get up to the 90, which we have to take into consideration. Our initial condition is just minus m naught, right? We just inherit the magnetization we had just a second ago. That's the unstable state. It's going to decay by e to the minus. And the time that we care about is the time from the first pulse to the second pulse. That's just ti. So e to the minus ti by t1, the tissue t1. That's the first term. The second term I need is just my return to equilibrium term. It always pretty much looks the same. So it's just m naught times 1 minus e to the minus. Same amount of time, the ti, time between the 90 and the 180 and the 90, divided by t1. We can add those terms together because we have some common exponential terms. And we can just write m naught 1 minus 2e to the minus ti by t1. And so this, this process here was the RF pulse, and this process here is just free precession. Let's keep track of what's happened to MXY. So we've got MXY. We want to talk about what's happening immediately before the second RF pulse. So event 2 immediately before. How much transverse magnetization? Still 0. Easy to keep track of. That's nice. The next thing we have to do, and I'll do it with my MXY magnetization, we have my MXY magnetization for time point 2, but immediately after. So now we've gotten out to our 90 pulse. We want to see what happens to the transverse magnetization. The transverse magnetization is going, because it's a 90, you're basically going to take your longitudinal magnetization and trade it off into your transverse plane here. And so the available magnetization is just the same term. It's m naught 1 minus 2e to the minus ti by t1. And this alludes back to Avanash's question. Here we had a state of the mz magnetization governed by t1 relaxation and how much time has elapsed. But now we played a 90, we pushed that magnetization into the transverse plane, and now we can sample it with an imaging experiment. We don't know how to do the imaging part yet, but we can see that it exists in the transverse plane at this point in time. And it's T1 dependent contrast in the transverse plane, just because we're flipping things back and forth, right? If we go back to the other side now, we want to say, well, what is mz for time point 2 immediately after the RF pulse? If we did a good job, meaning in this case, it doesn't matter. How much mz magnetization are we going to have? Just 0, right? It's just inherited from our transverse state, but our transverse state was 0. So we're going to carry this out just a little bit through a few more steps because we want to see where the solution sort of lands us. So that got us to the end of event 2, or immediately after event 2. Now we have to go through this period of evolution up to time point 3. So let's keep track of where our magnetization is now. Our MZ magnetization up until time point 2 was recovering, but it's unlikely to get back to M naught. So we'll just draw it as recovering to say there. Our MZ magnetization all the way up to time point 2 wasn't doing anything interesting. And then we suddenly played this 90 pulse where we had some MZ magnetization. And so we're going to inherit that magnetization. So our transverse magnetization is going to go up. And because it was a 90 pulse, our longitudinal magnetization is going to come down. So a few more time points to round it out. The next one is what happens to MZ magnetization immediately before time point 3. So now we're talking about what happens to the magnetization between the 90 and the 180. We're going to inherit our initial condition, which is just 0. That's going to operate on a term that we don't really care too much about because it's a 0, but it looks like e to the minus tr minus ti by t1. I'm not going to use this nomenclature because it's not that common, but per our diagram above, that tr minus ti is just td. When we work on the scanner, the parameters you'll see are the tr and the ti. We don't adjust the td. We adjust the tr and we adjust the ti. So I stick with those terms. This was just our decay of the prepared magnetization state. And then we still need our return to equilibrium term. So it's still m naught 1 minus e to the minus. And it just has a chance to recover during that interval tr minus ti. And of course, it depends on the t1. So that means our MZ magnetization from this time point here up to the 180 is going to recover. It wants to get to its equilibrium state of m naught, but it probably won't. And so we'll just draw it as magnetization that approximates or gets close to that. we need to look at what's happening to our MXY magnetization. So this is MXY for time point 3 immediately before. And here we just have as our initial condition the magnetization from the previous time point, just m naught times 1 minus 2e to the minus ti by t1. That's just the IC term. But our transverse magnetization now, this is just the initial condition. It has to decay according to T2 now. And so we have to have an e to the minus same interval, tr minus ti, ti divided by T2. And so this term here, just not to get confused, that term there is just the initial condition term. And then the equation of free precession says that whatever initial condition we had isn't stable either, and it's going to decay as a function of T2. And so that means that our T2 our transverse magnetization, of which we had a little bit, it's going to decay all the way until we get just before the inversion pulse here. And because T2s are short and the TD might be relatively long, let's just say that this magnetization goes down to 0. Almost there. Let's see how I do this. I want to keep my diagram, but I'm going to cover up some of the math. Were you guys caught up at that point? Mostly nods? Okay. So what we want to talk about now is what happens immediately after time point 3. We got to the magnetization immediately before. So we want to talk about our MZ magnetization immediately after time point 3, 0 plus. And that's just going to be inverted magnetization, right? We're going to take the state of our MZ magnetization, play a 180. It's going to invert itself, so we just add a minus sign. So we get minus m naught times 1 minus e to the minus tr minus ti by t1. And so that's just showing that our our longitudinal magnetization goes down to being inverted. We have to keep track of our MXY magnetization as well. So our MXY at time point 3, immediately after, in this case, the inversion pulse. We just have the amount of magnetization that we had before. The inversion pulse doesn't really do anything to the transverse magnetization. It flips it over like a pancake, like we said before. So it could be adding some phase, but we're not going to worry about phases right now. And so we just have the same state of our transverse magnetization. M naught times 1 minus 2 e to the minus ti by tr. By t1. And then this decay term, e to the minus tr minus ti. By t2. So this term was at 3, 0 minus was effectively 0 because of this term here. So this magnetization, the transverse magnetization immediately after this 180 pulse will be very, very, very low for typical timing parameters. Last thing I want to do, and it's only because it establishes something like a steady state, we get away from what happened during the first interval. And we're talking about what happens during this second interval, the second TR, if you will. We want to talk about our MZ magnetization as it approaches the 90 pulse again. So this is our MZ for time point 4 immediately before it. And so here we have This is our initial magnetization. It's going to decay according to a time ti, and then we'll have this return to equilibrium. So I'm just going to keep the magnetization I had in the previous step, minus m naught, 1 minus e to the minus tr minus ti by t1. Looks identical, but that's the decay term. That's going to go away depending on how much time has elapsed, which in this case is e to the minus ti by tr. I have a second term that I need to add to this as well. I'll write it just right underneath, and that's my return to equilibrium term. Still have to have it. And so that's just m naught 1 minus e to the minus ti by t1. What's that?
E to the minus ti over u rho tr.
Here,
Yes.
e to the minus ti over t1. Yep. Thank you. Okay, so what is that magnetization doing? That's just this magnetization headed back towards its steady, its final steady, or headed back towards some other value. And so it's going to recover as a exponential towards m naught, but it's only going to get to a certain state. We can do the same thing, of course. We'll just do this. Well, actually, let's simplify what's on the right-hand side here. And so this magnetization that's on the right-hand side here just reduces to having an m0 term times 1 minus 2e to the minus t I by t1 plus e to the minus tr by t1. There's some combination of some terms that gets us down to this point. Just wrapping up, we look at what happens to the transverse magnetization. We have the MXY magnetization. This is immediately before time point 4. We're going to have the magnetization that we had before. I'll just shorthand it as MXY time point 3 immediately before. That's our initial condition, right? So it's just this whole magnetization term into here. But now, as we get out to time point 4, that magnetization has to decay according to e to the minus ti by t2. We can collect some terms and see that this takes the form of m0 times 1 minus 2 e to the minus ti by t1 times e to the minus tr by t2. I did that right? And the point is that this term, again, this transverse magnetization term, immediately before, say, in this case, the 4th RF pulse, that's really something close to 0. This term here is going to drive the magnetization to be close to 0. So it's approximately 0 for the condition of T2 being much less than TR. So if we drew that out as we can, it's this one. Then after the after the 90 pulse at this point here, our longitudinal magnetization goes down to 0 because it was a 90 pulse. Our transverse magnetization doesn't do anything at the point of the 180, and then it's still very, very low. And when we play the 90 pulse, then we can tip this magnetization up into the transverse plane. So we didn't work it out, but we could have talked about what was MXY at time point 4 immediately after. And you guys can get that from the state of the magnetization, the MZ magnetization immediately before the pulse. Okay. There's a little bit of algebra in some of those steps that I didn't go through carefully, combining exponential terms. Hopefully you can work that out on your own. Let me know if there's a problem with that. What I want to do in just the last couple minutes, and then we'll field some questions for the homework, is just talk about what the result of this expression really means, as we did for the saturation expression.
And we'll come back to the examples I have at the beginning of the next lecture. So what I'll show you in just a second is coming back to the state of our NZ magnetization, or what could be our transverse magnetization after that second 90 pulse. And so we'll have that the amplitude of the signal that we would measure, it's still going to depend on proton density, because things always are mapped according to proton density. This is that M naught term, if you will. And now it depends on a couple different things. It depends on the TI and the T1. And it also depends on the TR and the T1 in that final expression of the magnetization. We could form an image. An image is just intensities as a function of space, and that'll be proportional to the proton density as a function of space, as well as the T1's function of space. So T1's not going to be constant at every pixel, nor is the proton density. So what's nice about this expression is that the final image is the product, again, of some proton density function and some T1 weighting function. And that we have two possible ways of controlling contrast now. We can adjust the TI or we can adjust the TR. And that just gives us more flexibility or more control over overall image contrast. There are some definitions for how we can sort of choose our TI times, for example. So if you have a target T1 in mind, this is the nomenclature Lauterbur uses. So you know the T1 of something is 500 milliseconds or close to that, or you know it's 900 milliseconds. Then you might say, well, what inversion time should I use so that that particular tissue is null? If you want to figure that out for yourself, it follows out of the expressions we were just working with. But you can calculate that it's basically log 2 times the T1 of the thing you care about. I think this will be helpful. I forget if we use this in the first lab or not. You might need this expression in the first lab experiment that we'll do, where you can get a quick guess at an inversion time based on knowing something about the T1. So in the limit of TR being very, very long, some terms drop out, this term in particular, and you just end up with log 2 times T1. So that's one way of being able to dictate that the image intensity will be close to 0, where pixels have a T1 equal to your target T1, using the TI that you get from this expression. Just a quick comparison of saturation versus inversion recovery. We basically kept track of the magnetization during what happens after a saturation pulse and what happens after an inversion pulse. The difference in what we did with the inversion pulse is we said we're going to invert the magnetization, but then we're going to generate with that 90 pulse some transverse magnetization that we could use to form an image. We didn't talk about forming echoes yet. That'll be sort of the next step. There'll be another RF pulse that we add when we come back on Friday. So as it's 2:50, I think what I'll do is hold off on the applications slides here. We'll come back to those because it's just a few slides. Yeah, I'll come back to those at the very beginning of the next lecture, just to introduce some conceptual applications of sat pulses as well as the inversion pulses. So with that in mind, then the lecture is done for today, and we can have some discussion until someone pokes their head in if there's another lecture, and field questions about the homework. Okay? Okay. So questions about the homework? Patrick is here. I'm here. You could come up individually. Some people have handed in the assignment already. It sounds like office hours and emails have been pretty busy.
Yeah. So, yeah, just come ask me any questions you have. If someone kicks us out.
Okay, we're here. If there aren't questions for the group, then just come up one by one if you have them. And remember, we have lecture Friday.